Here are two antennas, an electric sensor, a whip antenna, and a magnetic sensor that's a loop antenna. They are standing far enough from the house to be free of the fields inside the house, at least essentially free. Let's see. The loop antenna has a primary winding, a single turn, low inductance. You can see the thick copper and large areas on the conductors going to it. That's because the coil, the single turn with a diameter of 0.7 meter from sheet metal, has a very low inductance, and I want to maximize the current by making the inductance small everywhere. The toroid has a winding with about 40 turns, connected one side to ground and the other to the gate of a FET transistor, a J310. There is a single turn from source through a capacitor and a resistor to ground to give current feedback. That makes the impedance extremely low for current going through the toroid. This means that the loop is essentially short-circuited by the transistor amplifier. And then there is a bipolar afterwards to bring up the signal level a bit. This antenna should be insensitive to electric fields, but I will show that it is not. The antennas are connected to this box, which supplies 12 volts on the center conductor out to the antennas. The box has a filter to make sure that no interference can enter from the power supply. The cables go to this box. It's a Fedri SDR net. It's a 2-channel receiver. The SDR net is powered from the USB only, like that. There are no precautions inside for interference suppression. It wouldn't help. This is BBC, 252 kilohertz. There is some horrible switch power interference, as you can see. Now I'm listening to the magnetic antenna. I will switch to the electric antenna here. And they sound very similar, both antennas. If I tell Linra to try to optimize, it will use both signals. The problem is conducted interference. I will insert isolation circuits here. This will prevent current from flowing on the outside of the coaxial cables. That isolator only changes to this situation. In the S-meter graph, the red is the magnetic and the blue is the electric sensor. I'm listening now to the electric, and here is the magnetic. And both have good quality, and it's not so easy to say which one is better or worse. So I click on the noise floor here. And here now I take away the AGC by reducing the gain. And here is the magnetic, and here is the electric, very much the same as you can see in the baseband window here. When I step upwards in frequency, well, that was too far. Let's go. Here is something. It's an interference of some kind. And the electric antenna and the magnetic antenna, it's present in both of them with similar amplitudes. Voltages on the coaxial cable, they go into this PCB and couple capacitively to the sheet metal of the loop, and it also couples from the windings on the toroid to the center contactor through the toroid. If the loop stands directly on the ground, there is also a capacitance to ground. And if it's not symmetric and very well balanced, there is a voltage induced in the turn, the single turn coil. So I moved it about 1 meter up from the ground, and I will remove the isolation circuit from both antennas and compare them. This interference at 840 kilohertz is of course much worse now. When I removed these isolation toroids again, if I go back to BBC 252 here somewhere, we don't hear much. So this is the electric field. And this is the magnetic. And you can hear, now it's better than it was before. This is the improvement you get by using a magnetic sensor. If you just use it without precautions on conducting interference out to it. So I will insert the isolators again. Now I'm listening to the whip antenna. That's the blue track on the S-meter here, or the green dots in the baseband spectrum. The red or magenta is the magnetic sensor. As you can see, the signal is very much the same with both antennas. If I click on the noise floor, let's say here, you can see that the noise is very much the same in both antennas. Or on the low side it seems a little bit weaker. But the noise level is very much the same. Now I can tell Leanrad to combine the two signals, and you can see the signal goes up while the orthogonal combination, which is the noise, it goes down. So rather than having from here to here a signal to noise level, I have it now from here up to here. So although the noise is the same, it's uncorrelated. It comes from different parts of the sky because the radiation patterns are different from the two antennas. So I go up in frequency. Here is some interference problem. And this is the electric field, the whip antenna. And here is the magnetic field. And this interference is here, but it's clearly weaker. So there is some suppression by the antenna now when I lifted it from the grass and placed it about 1 meter higher up. The isolators provide a high impedance for currents on the screen. In a 50 ohm system they attenuate by about 40 decibels, or this low maybe 50 dB or so. I have now connected a ground point, these copper tubes that are down about 0.5 meter into the ground. They now connected to the screen of the cables going away here towards the antenna. Introducing the ground on the far part of the coaxial cable has changed the behavior. I'm listening now to the magnetic, which is in blue here, but the electric is no longer much worse than the magnetic interference. So this could be a little bit hard to understand. Why does this modification affect the two antennas differently? Moving the antennas further away from the house does not make any difference at all. But here I have put a second toroid isolator in the cable to the whip antenna, just near the antenna. And you can see the blue track is now much better than the red one. I will have to put an isolator near the magnetic loop also. Now there are interference isolators near both antennas, and you can see this interference is still there. The noise floor, if I go a little bit on the side, is rather similar. Red here in the S-meter graph is the magnetic antenna, and blue is the whip antenna. If I go on the interference, it is clearly stronger in the magnetic sensor. I can go down to BBC again, to 52. That's here. And you can see the level is very similar. I can make it identical by changing the voltage a little bit. That will lower the gain of the magnetic amplifier, while the electric is unaffected. So here the signal is the same. And the noise floor also. Going upwards in frequency, Somewhere here is an interference, and you can see it is a little bit stronger magnetically than electrically. I connect this adaptive polarization, and you can see that it is really an interference, because when it combines like this, the combination that gives minimum signal is about 14 dB below the combination that gives maximum signal. So I can select the opposite polarization like that. So now I'm listening to medium wave with a null in the direction of this interference source. It's my neighboring farmer. It's about one wavelength away, so there has to be both a magnetic and an electric field, and I can combine them to make this problem disappear. That will create a maximum lobe that is perpendicular to the direction of the farmer. And it depends, of course, how the magnetic sensor is oriented. I could orient it for a null in his direction, and then I would have no use for the signal from the whip antenna. Further up in frequency, at this time of the day there is not much, but here is an interference, and I go for here the electric is the blue and the magnetic is the red, and they look very much the same. And I click at the side of this interference, and you see, so this interference is electric as well as magnetic, and with the same magnitude. And the time now is 3 o'clock in the afternoon. Both antennas are now far away from the house, and they are no longer disturbed by conducted interference. I will move them closer to the house to see how far away they actually have to be to avoid most of the interference that come from my own house. The antennas are now about 15 meters from the house. For some reason the magnetic signal is a little bit weaker than the electric signal. I don't know the reason for that. There is no obvious interference visible, so I continue up in frequency. And this interference is about as it were before. And the farmer QRM is here. There is not much difference from having the antennas much further away from the house. I will now move them a little bit closer. Both antennas are now about 8 meters from the house. There is some interference, but the quality from this BBC transmission, 252 kilohertz, is not very different from what it was before with the antennas far away. If I click on the noise floor here, I can see interference lines. This is typically local QRM, and here it's more obvious. upwards in frequency. It's a little bit unclear what is interference local and what is something coming from far away. This interference, I now listen to the whip antenna, and here is the loop antenna. And you can see the loop is picking up less of this interference. That of course depends on how it is turned to some extent. It's pointing towards England, so it is 45 degrees towards the house. It seems 10 to 15 meters is a distance that one should try to reach if possible.